Hello everyone, welcome to my presentation which titled Eco-Friendly Luffa Fiber Epoxy Composites for Improved Thermal Insulation in Wall Applications. This study develops a sustainable Luffa fiber epoxy composite investigating how the fiber particle size and particle substitution of epoxy with natural resin from uh, Comifora Abyssinia affect thermal insulation, mechanical strength, and physical behavior of wall applications. My name is Ahmed Al-kamal. I'm from Mustan University in Baghdad, Iraq. Building account for sustainable share of global energy consumption with heat again loose through exterior walls representing one of the main pathways of thermal exchange between indoor and outdoor environments. For that, this has driven increasing global demand for sustainable and environmentally friendly insulation materials capable of reducing the energy footprint of built environment and has led to significant research efforts toward the development of bio-based composite systems. The limitation of conventional epoxy. These epoxies are widely employed in engineering and construction applications due to their excellent mechanical strength, chemical resistance, and durability. However, the reliance on non-renewable petroleum resources and their non-biodegradable nature have raised serious environmental concerns, especially in the context of global warming and pollution associated with industrial production. For that, the search for alternative wall materials that combine thermal insulation efficiency with environmental sustainability has become a priority in materials science. For that, natural fibers have emerged as promising candidates for reinforcing composite material due to their low density, renewability, and economic advantage. Why we use Luffa cylindrica? Due to their unique structure characteristic, because they have high porosity, sponge-like architecture structure that enable efficient energy absorption and provides favorable thermal insulation properties. This cellular structure is comparable to engineered materials such as metallic foams, which are known for their ability to dissipate mechanical loads effectively. Additionally, Luffa is widely available, fast-growing, and environmentally benign, making it an attractive reinforcement material for sustainable composite development, particularly for eco-friendly wall insulation systems where low thermal conductivity and reduced material density are desirable. Despite these advantages, the integration of natural fiber into polymer matrix presents several challenges. The primary issue arises from the inherent incompatibility between hydrophilic natural fibers and hydrophobic synthetic resins such as epoxy. This mismatch leads to weak interfacial bonding, resulting in poor stress transfer efficiency and reduced mechanical performance of the composite material. Previous studies has highlighted that morphology and distribution of fiber scientifically influence the overall behavior of composites. In particular, fiber size and shape play a critical role in determining dispersion, interfacial adhesion, and void formation within the matrix. Grinding natural fibers into controlled particle size has been shown to improve homogeneity and enhance the interaction between the fiber and matrix faces. For that, hybrid composite strategy when you use natural resin substitution. Recently, researchers have increasingly focused on hybrid composite systems that combine natural fibers with both synthetic and bio-based resins to achieve a balance between performance and sustainability. A partial substitution of synthetic resins with natural resins represents a promising approach for reducing environment impact while maintaining desirable material properties. For that, we use natural resin sources that derive from the Commiphora species, exhibit adhesive, viscous, and film-forming characteristics that can improve compatibility with the composite system. These materials contribute to reducing the carbon footprint of composite production and promote the development of eco-friendly materials. Thermal and interfacial benefits. Several studies have demonstrated that incorporating natural resins into polymers composite can enhance certain thermal properties and interfacial bonding characteristics. Natural resins may improve compatibility between hydrophilic fibers and hydrophobic epoxy matrix. We have also mechanical trades-off. The mechanical performance of such composite is highly dependent on the substitution ratio. While moderate replacement levels may improve compatibility and sustainability, excessive substitution can lead to decline in mechanical strength due to reduced matrix continuity and structural integrity. Therefore, identifying the optimal balance between synthetic and natural resins content is essential for achieving performance hybrid composites. The research gap in this project that combine effect of fiber particle size and resin composition has not been extensively investigated, particularly for Luffa fiber-based composites. Most existing studies have focused either on fiber performance or resin modification independently without addressing their interaction. Understanding this interaction is critical as both factors directly influence key properties such as thermal conductivity, compressive strength, hardness, and water absorption behavior. For that, we prepare the composite by using Luffa fibers, which obtained from local markets in Baghdad and utilized as a natural reference due to their low density and porous structure. Commercial epoxy resins and its corresponding hardener were supplied from a local construction material provider and used the primary polymer matrix. Natural resins derived from the Commiphora was employed as partial bio-based substitute for epoxy due to its adhesive and film-forming properties. The Luffa fruits were manually cleaned to remove seeds and impurities, followed by washing with water to eliminate dust and contamination. The fiber were air-dried for 48 hours and subsequently oven-dried at 80 centigrade for 80 minutes to remove residual moisture. During oven drying, the samples were periodically rotated to ensure uniform heat distribution. After drying, the fiber were mechanically ground and sieved into three particle sizes ranged from 1.2 mm to 4 mm using standard sieve shaker. A secondary drying step was conducted for 60 minutes after grinding to further reduce moisture content prior mixing. And for that, the composite fabrication was carried out using weight-based ratio to account for difference in density and morphology for Luffa fibers. The epoxy resin and hardener were mixed at the ratio of 1:1. Luffa fibers were incorporated as a constant content of 10% relative to the epoxy matrix for all composites. The natural resins was produced as a partial replacement for epoxy at weight fraction of 5, 10, 20%, while maintaining constant total mass. After that, a prepared mixture were poured into cylindrical molds for the compressive strength testing. Additional specimens were prepared for hardener, water absorption, thermal conductivity, and microstructural analysis. All samples were cured under ambient laboratory conditions until complete solidification. For that, we test compressive strength, hardness, water absorption, thermal conductivity, and SEM. All composites were prepared based on weight ratio to account for different in density, fiber porosity, and regular morphology, ensuring more accurate representation of real materials behavior. So we have the sample code with description. For example, sample A represents pure epoxy, AB1, AB2, AB3 represent epoxy Luffa fiber at different sizes. AC represent epoxy plus natural resins at 5, 10, 20%, and so on. Our results shows that the heat epoxy samples exhibit a compressive strength of 76 megapascal. The incorporation of Luffa fibers led to considerable improvement in strength, particularly for the composite containing 2.36 millimeter fiber AB2, which achieved the highest value of 135 megapascal. This enhancement can be attributed to the optimal balance between the surface area and dispersion at this particle size, resulting in improving the interfacial bonding and efficient stress transfer. In contrast, composite reinforcement with finer particle exhibit lower strength due to particle agglomeration caused by their high surface area, leading to the non-uniform dispersion and weak interfacial region. However, the addition of natural resins led to a gradual reduction in coercive strength, as observed in AC5, AC10, AC20 samples. This reduction can be attributed to the lower stiffness and cohesive strength and natural resins compared to the synthetic epoxy matrix. However, in hybrid composite, the presence of Luffa fibers mitigate this effect. Notably, the ABC2 series exhibit higher strength compared to their hybrid compositions, indicating that optimal fiber particle size enhance compatibility and low transfer with the composite systems. Hardness values shows a slight decrease with the incorporation of Luffa fibers due to their porous structure and less rigid structure compared to the epoxy matrix. The net epoxy exhibit the highest thermal conductivity, attributed to its dense and continuous structure that facilitate heat transfer. The incorporation of Luffa fibers resulted in this significant reduction in thermal conductivity due to the porous structure and the presence of entrapped air, which act as an effective thermal barrier. However, the addition of natural resins further reduced the thermal conductivity, which may be attributed to its lower thermal conductivity compared to epoxy and is role for improving the interfacial compatibility. In hybrid composite, the lowest thermal conductivity was observed in the ABC2-20 samples, confirming the synergetic effect between optimal fiber size and natural resins incorporation. However, the water absorption also shows the lowest value for the net epoxy at 0.36%, attributed to its dense and hydrophilic structure. In contrast, the incorporation of Luffa fiber significantly increased the water uptake due to their hydrophilic nature and the presence of epoxy OH groups in cellulose and homogeneous. The FTIR illustrates the chemical evaluation for net epoxy fiber and hybrid composite, and we have the spectrum of OH and CH and COC, and this composite at the hybrid natural exhibit further broadening and increased intensity of the OH bond, indicating enhanced hydrogen bonding interaction between the fiber epoxy and natural resins. For the SEM, we have the fine particles tend to cluster due to their high surface area, forming localized dense regions surrounding the voids. And also at the hybrid ABC210, the macrostructure shows improved matrix continuity and reduced void content compared to the fiber composites. We conclude that the best hybrid composite that ABC220 samples achieved low thermal conductivity and reduction of about 35% to the epoxy, and also compressive strength of 97.4 MPa remains adequate for the wall applications.